What up, chemistry people? Mr. Boylan here. Today we start our new unit. We're going to talk about thermochemistry today, and we're going to begin by defining the process of kinetic energy transfer at the particulate scale as heat transfer, and explain how calorimetry is an experimental technique that is used to determine heat exchanged/transferred in a chemical system. And as always, we're going to break that down a little bit. First thing we're going to do is talk about the relationship between temperature and kinetic energy, that is, the energy is motion. We're going to explain how heat is the transfer of kinetic energy from one object to another. We're going to manipulate a formula for heat, Q equals MCAT, which you may recall from your first year chem class, also known as MC delta T, and solve for any variable. And then lastly, we're going to talk about how the lab process of calorimetry is a fun one, but also how we can use it to determine the change in heat energy during a chemical reaction or a phase change. So it's going to be a thriller. Hopefully a lot of this stuff is review from your first year chem class. But let's take a look. All right, so first up, we're going to talk about temperature, which is simply the measure of the average kinetic energy of the particles of a substance, or essentially how much energy of motion that substance possesses. Couple of things to keep in mind about temperature. One, the Kelvin temperature is proportional to the average kinetic energy. In other words, the hotter the temperature is, the greater the kinetic energy is. Or conversely, the colder it is, the less kinetic energy your sample has. Second point to think about as we think about temperature. As we approach absolute zero, or 0 Kelvin, the particles approach zero kinetic energy. At that point, all molecular motion comes to a stop, theoretically. Third point to keep in mind, we're going to use what are called Maxwell-Boltzmann distributions, which just show us how the particles at high temperature have greater kinetic energy than those at lower temperatures. Sounds like a tricky concept because of the names, but it's just a pretty easy graph that indicates when you are at lower temperatures, in this case 300 Kelvin, the majority of your particles will have a lower molecular speed than when you, or lower kinetic energy, than when you have your temperature at 1000 Kelvin, where the majority of your particles will have a much larger speed or larger kinetic energy. Maxwell-Boltzmann. The fourth thing to keep in mind is that we're going to use particle diagrams with vectors. Vectors can be used to illustrate the different kinetic energies at different temperatures. As you take a look at the image on your screen, on your left, you've got a low temperature substance, gas probably, and check out those vectors. Not a huge amount of kinetic energy, but check it on the right. High temperature substance, whoa vectors, whoa. Really a lot of kinetic energy there, really high temperature, insane. Be familiar with interpreting these diagrams and using the vectors to explain how much kinetic energy the given sample has. Woo! Okay, we're going to take a quick time out and listen to this thriller of a video.
At any given temperature, the molecules of a gas are in continual motion. At any instant, some molecules have more kinetic energy of motion than others. With increasing temperature, the average kinetic energy increases in proportion to the absolute temperature. This graph shows the distribution of molecular speeds for a particular gas at two different temperatures. Notice that the most probable molecular speed, given by the peak of the curve, increases as the temperature increases. Here we see a mixture of two gases with different molecular masses, helium and neon. The more massive neon atoms move more slowly, but they possess the same average kinetic energy as the helium atoms. At a given temperature, the distribution of molecular speeds for helium is much more spread toward high speeds than for neon. As the temperature increases, the average speeds of both helium and neon atoms increase. At any given temperature, their average kinetic energies are the same.
All right, so let's get back to the good stuff. We're going to talk now about heat. When that kinetic energy is then transferred from one object to another, that energy transfer is called heat. When molecules that have different temperatures collide then, that kinetic energy is transferred from the warmer substance to the cooler one until the temperature or average kinetic energies are the same. When we do reach the point where the average kinetic energies are the same, we say we have reached what's called thermal equilibrium. Third important thing to think about when we think of heat is something called specific heat capacity. It's most easily thought of as the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. You're given a quick data table there of just a few substances and their specific heats. Really important to take note of that metals typically have very low specific heats. Water, notably, has a really high specific heat, and that is important, or as you think about what that means, essentially you've got a lot of energy required to heat every gram of water 1 degree Celsius, but relatively little amount of heat is required to heat a metal substance up, 1 gram of a metal substance up 1 degree Celsius. A great way to think about this, or how I sort of keep specific heat straight in my mind, is I think about apple pie. Right out of the oven, you really want to dive in there. You get that gushy, warm center and that flaky golden crust. The gooey center's got a high water content. And so maybe if you are really hungry and you want to dive into that apple pie and you test the crust and you're thinking, oh, this is cool enough, I can totally eat this. And then you bite into it and you burn your mouth. It's because the specific heat of water is so high. So not only does it take a lot of energy to heat that water up, but then it's also going to take a long time for the water to sort of release or lose that energy. This is also really common if you're a Pop-Tart fan, or you like those pizza rolls. Anything with a gooey, watery center, but a not watery, crusty outer layer. Really good idea of what's going on with specific heat. We are then going to be able to measure the amount of heat transferred using the following equation. And this is where we get that Q equals mc delta T, commonly referred to as MCAT, where Q is your heat transferred, M is the mass of the substance, C is the specific heat capacity, and delta T is your change in temperature, your final temperature minus your initial temperature. Some things to keep in mind as we start working through some problems here. When you have a positive delta T, your sign of your heat is going to be positive, which simply indicates that heat has been transferred into the object. However, if you have a negative delta T, you're going to have a negative sign of Q, which simply indicates that the heat has been transferred out of the object. Again, so those signs are just telling us what's going on with the movement of the energy. You can't have necessarily a negative energy unless you're a negative person, but just telling us what's going on with the flow or the transfer of that heat energy. Okay, and then lastly, calorimetry is the experimental technique used to measure the change in energy of a chemical reaction or a phase change. Hace calor. ¿Quién habla español? Porque aquí hace mucho calor. Calorimetry, calor, is an experimental technique used to measure the change in energy of a chemical reaction or a phase change. And as we think about calorimetry, the big idea here generally is you put a chemical reaction or a phase change in contact with a heat bath. And usually that heat bath is going to be water. And we can then measure the temperature change of the heat bath, again, typically water. And because we know the heat capacity of the heat bath, which is, again, typically water, and the specific heat of water is 4.18 joules per gram degree Celsius, which is not on your formula chart, but a really good specific heat to memorize and keep in your noggin because we're going to use it so much as a heat bath. And then you can calculate the interchange from there. Keep in mind that the energy change in the heat bath is going to be the same magnitude or the same size, the same amount of energy as the chemical reaction or phase change, but with the opposite sign. So if the heat bath gains energy, its temperature is going to go up, meaning the energy of the chemical reaction or phase change went down, that it lost energy, and vice versa. So keep that in mind. You'll see Q and negative Q. It's just indicating what is going on with the flow of that heat. And then lastly, typically, and hopefully you remember this from first year chem, we use styrofoam cups as our calorimeters. They're pretty cheap. They're pretty good insulators. And so we can perform those reactions and not lose a whole lot of energy to the surroundings.